Good morning, students. Welcome to Chemical Crystal Palace. Today's topic of discussion is hybridization. We always have a question in our mind that why do different molecules have different shapes? This is due to hybridization. This concept of hybridization was introduced by Pauli. We can define hybridization as the intermixing of the atomic orbitals of same or slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent shape and energies. What does this mean? Basically, it means that in the process of hybridization, what happens is the atomic orbitals which are of the same energy or slightly different energies, like think it has to be of s and p orbitals which has the principal quantum number same. If it is of 2s orbital, it has to be 2p orbital, or the same energies like the p and p orbitals or the s and s orbitals can intermix together. These are the atomic orbitals. When they mix together, they form hybrid orbitals, and that time when they form hybrid orbitals, the orientation of these hybrid orbitals are completely different than the parent atomic orbitals, and the energies of each hybrid orbitals are equivalent. Now, some of the important characteristics of this hybridization are the number of the hybridized orbitals is always equal to the number of atomic orbitals that get hybridized. For example, if we have one s orbital and three p orbitals taking part in hybridization, these are the atomic orbitals. When they form sp3 orbitals, the number of the sp3 hybrid orbitals formed is 4. They form 4 sp3 hybrid orbitals because 4 atomic orbitals are involved in hybridization. Point is, the shape and the energies of the hybridized orbitals are equivalent. Like if 4 atomic orbitals, that is 1 s and 3 p orbitals, are mixed together to form sp3 hybrid orbitals, the orientation and the shape of this sp3 hybrid orbitals, which we'll learn a bit later, will be same for all the 4 hybrid orbitals. The next point is the orientation of the hybrid orbitals are in some preferred direction such that there is minimum repulsion of electrons. Slowly we will see the different hybrid orbitals, the sp3, sp2 and the sp hybrid orbitals, and we'll see the different geometry, different orientation in which they are in the 3D space. They prefer such orientation so that the repulsion between the electron clouds are minimum so that they can remain stable. The first example we take of one s orbital and one p orbital combining to form two sp hybrid orbitals. We know that the shape of s orbital is spherical and p orbital is doubled shape. It forms a new orbital, that are two hybrid orbitals with a different orientation. These are equivalent in energies. So the first important characteristic of hybridization is maintained, that is, the number of the hybridized orbitals is equal to the number of atomic orbitals that get hybridized. Here the number of the atomic orbitals are 1s and 1p, that are 2 atomic orbitals, and 2 sp hybrid orbitals are formed. We know that there are 3 p orbitals and each p orbital has its own axis. This p orbital is along the x-axis, this is along the y-axis, and this is along the z-axis. In case of sp hybridization, we take the px orbital. Hence, we can say that hybridization, by the concept of hybridization, we can explain the geometry of a particular molecule, be it organic molecule or inorganic molecule. Today we will learn about 3 types of hybridization, that is sp3 hybridization, sp2 hybridization and sp hybridization. In sp3 hybridization, 1s and 3p orbitals are atomic orbitals are involved to form 4 new HO. What is the meaning of HO? Hybrid orbitals. In sp3 hybridization, as one s orbital is involved, so the amount of the s character is 25%, and the 3p orbitals are involved, so the amount of p character is 75%, in order to make this together total 100%. In case of sp2 hybridization, 1s and 2p or atomic orbitals are involved to form 3 new sp2 hybridized orbitals. In case of sp2 hybridization, 1s and 2p orbitals are involved to form 3 new hybrid orbitals. So as 1s atomic orbital is involved, the percentage of s character is 33.33% of s character, and 2 atomic or p orbitals are involved, so the percentage of p character is 66.66% of p character. In case of sp hybridization, only 1s and 1p atomic orbitals are involved to form 2 new sp hybrid orbitals, so the amount of s character is 50% and the amount of p character is also 50%. Now we take an example to explain each type of hybridization. First comes is sp3 hybridization. We take an example of a simple molecule, that is methane CH4. We know that the electronic configuration of carbon with the atomic number 6 is 1s2, 2s2, 2p2. And in the ground state, the electron distribution is in the 1s orbital 2 electrons, 2s orbital 2 electrons, and in 2p we have 3 orbitals which we denote as px, py and pz. As only 2 electrons are there, the 2 electrons are distributed in the px and the py orbitals, and the pz orbital is vacant. When carbon is in the ground state, the electron distribution is this. And now when carbon is going to form the molecule CH4, that time it goes to the excited state, in which one of the electrons from the 2s orbital is promoted to the pz orbital, which was vacant before in the ground state. As a result of which, the 2s and all the 3 p orbitals are singly occupied, and these 4 orbitals will take part in hybridization, that is 1s, and 3 p orbitals will take part in hybridization, as a result of which 4 sp3 orbitals will be formed. The shape of s is spherical, and p, we take the first one to be px. This is px. This is py. And then the pz orbital. These 4 combine together to form 4 hybrid orbitals, that is 4 sp3 orbitals. The shape and the orientation of these sp3 hybrid orbitals in the CH4 molecule will be smaller lobes for the s orbital also, but it is not shown in order to avoid dinginess of the molecule. This can also be represented with carbon at the center and the 4 bonds. The bond angle between each bond in sp3 hybridization will be 109.5 degree. This side also it's 109.5 degree. Here also the same. 109.5 degree, 109.5 degree. They are oriented in such an angle so as to avoid the minimum amount of repulsion, that is the electron cloud repulsion can be minimized when they are oriented at 109.5 degree angle to each other. Now, the methane molecule is formed by the combination of the 4 hybrid orbitals, that is the 4 sp3 hybrid orbitals along with the 1s orbital of hydrogen. These are the 4 sp3 hybrid orbitals of carbon. It combines with the 1s orbital of hydrogen to form the methane molecule. From hydrogen there is the contribution of 1 electron, and from sp3 orbitals there is 1 electron. 2 electrons in each of the sp3 and 1s orbitals of hydrogen combination. The shape of the sp3 molecule or the sp3 hybridized molecule is tetrahedral. This was an organic molecule. Methane was an organic molecule. We can take examples of other inorganic molecule like NH3. Here the lone pair of electrons on nitrogen also take part in hybridization. Water. Here also the lone pairs, the two lone pairs of oxygen take part in hybridization. Coming up to the next step of hybridization is Sp2 hybridization. We take example of the simple molecule, that is ethene. Here also carbon with atomic number 6 has the electronic configuration 1s2, 2s2 and 2p2. In the ground state, the electrons are distributed like this in the 1s orbital, 2 electrons, 2s orbital, 2 electrons and 2p orbital, also 2 electrons in the px and the py orbital, and the pz orbital is vacant. When carbon is in the excited state during the formation of the molecule, the electron from the 2s orbital, one of the electrons from the 2s orbital is promoted to the 2p orbital, and now 1s and 2p, that is px and py, 1s and 2p orbitals will involve in hybridization to form 3 sp2 hybrid orbitals. This pz orbital will not take part in hybridization and will remain as unhybrid orbital. One s and 2p, px and py orbitals will combine to form the 3 sp2 hybrid orbitals. The orientation will be the smaller lobes are from the s orbitals, and they are and the shape is planar. These orbitals are situated at an angle of 120 degree to each other in order to reduce the electron cloud repulsion between each other. At 120 degrees to each other, the bonds are stable. This is the ethene molecule, in which this is CH2 group, C and H2 and C and H2. These are the 3 sp2 hybridized orbitals of this carbon, and these are the 3 sp2 hybridized orbital of carbon. And this is one entire unhybridized orbital, the pz orbital, and here also the pz orbital. These sp2 hybridized orbitals of carbon overlap with the 1s orbital of hydrogen to form the CH bonds, and this is the bonding between the sp2 hybrid orbitals of the two carbon atoms to form the sigma bond here. Here also sigma bond is formed, here sigma bond, 1s sp2 sigma bond, 1s sp2 sigma bond. But the pz of this carbon overlaps with the pz of this carbon laterally to form the pi bond. This is the pi bond. So when we write the ethene molecule, we write CH2 double bond CH2. In this double bond, one of the bond is pi bond and one of the bond is sigma bond. Hence, this is the structure of ethene molecule. Other examples of sp2 hybridization can be of any carbocation. We take example of methyl carbocation or an inorganic molecule like BCl3. These all undergo sp2 hybridization. The third type of hybridization which we come across is sp hybridization. We take example of ethyne. Again, the electron distribution of carbon is 1s2, 2s2, 2p2. In the ground state, one of the pz orbitals is vacant and two of them are singly occupied, that is the px and the py. In the excited state, that is during the formation of the ethyne molecule, one of the electrons from 2s is promoted to the pz orbital, and now this ethyne molecule undergoes sp hybridization, that is 1s and 1p orbital combine. 1s and 1p. Take, for example, we take px to form 2 sp hybridized orbitals with linear structure. These are the sp hybridized orbitals. As 2 atomic orbitals are involved, so 2 hybrid orbitals are also formed. Remaining py and pz orbitals are unhybridized. Here, in case of ethane molecule. Now when ethane molecule is formed, there are 2 carbon atoms. The general formula is CH triple bond CH. For 1 carbon atom, we have 2 sp hybridized orbital, and here for this also 2 sp hybridized, here 2 sp hybridized. This sp hybridized orbital combines with the 1s orbital of hydrogen. Here also the same, it combines with the 1s orbital of hydrogen. The bond formed here is the sigma bond, here the sigma bond. These 2 are the sp hybridized atomic orbitals. This also formed the sigma bond. The remaining py orbitals unhybridized, one here and the other here. These atomic orbitals, the py orbital, there were 2 unhybridized atomic orbital, that is the py orbital and the pz orbital. These 2 combine together. The py combines with the py of this carbon. Make sure that the py will never combine with the pz, because the orientation is different, that is they are perpendicular to each other, so they can never combine together. The py has to combine with the py and the pz has to combine with the pz. So this forms the 2 pi bonds. The py bond is 1 pi bond and the pz bond is the other pi bond. So the molecule of ethane is CH triple bond CH, in which 1 bond is sigma bond and 2 bonds are pi bonds. The structure of or the orientation of sp hybrid molecules are linear. The geometry is linear. Other molecules which are of sp hybridization can be your BeCl2, MgCl2, etc.